So hey nerds, this is Suman, and in this video I'm going to show you the exact form of the second equation that I had already derived in my first video. So basically in last lecture we have discussed about the Heisenberg uncertainty principle in terms of position and wavelength uncertainty, right? So I had used the kinetic energy based idea in order to show the connection between the position and momentum in terms of Compton wavelength. If you had seen that, this video is going to be more helpful to you, and if you hadn't seen that video, you can actually see this video. You will understand both of that, because the first thing that I had already derived in my previous video is the special case of this particular mathematics, so I can show you that. So basically I'm very excited to show you that, and again I'm telling the same thing that I already previously said in my video, that I didn't invent anything. This is not my theorem. I just manipulated the terms and terminology and get the another result, where I had connected u with the uncertainty relation with wavelength term, the momentum term, the energy term, and at the end the gamma factor term, that is the Lorentz factor. And at the higher speed the Lorentz factor came into the play. They are actually devil of physics, right, in relativity. So they actually do have some their importance. So basically I had actually take out the printout of my two papers. I'm not saying that my paper, just I have taken out the printout for the better intuition and for the learning process, and something that I can also again manipulate it, and I had printed out it. So without wasting your any time, let us dive into the whiteboard. So hey nerds, so I'm again starting from the same idea that I have already done in my previous idea, but in terms of relativity. So I'm using the relativistic energy term equation. So you can ignore the background because knowledge is more important than the noise. So basically what Heisenberg tells us that from uncertainty relation, from uncertainty relation we have delta x into delta p is greater or equal h upon 4 pi. So this is the first equation that you have to know, and you might have already seen in your higher level classes. That is the famous equation showing the quantum nature, quantum behavior of particle. If you try to confine the particle in a position with a very high degree of uncertainty, then the momentum will spread out. If the uncertainty goes on decreasing, if this uncertainty goes on decreasing, the momentum goes on increasing, and vice versa. So, and another thing you have to know is the de Broglie hypothesis. De Broglie hypothesis. Yeah, de Broglie hypothesis. So according to de Broglie hypothesis, you can write momentum is h upon lambda. That is the wavelength, and sorry, that's the old-fashioned Planck's constant, very famous Planck's constant, and this term. So you can write momentum is h upon 2 pi into 2 pi upon lambda. So I just manipulated some things here. So p is equal to nothing, but you can write h upon 2 pi is reduced Planck's constant, that is h squared, and 2 pi upon lambda can be written as k, the wave number, I guess. So I am just lagging here both times. So this would be my equation number second. So using 2 in first. So what will I get? Delta x into delta h squared k is greater or equal to h upon. So I can write it also in terms of reduced Planck's constant, h squared upon 2. It makes sense. So delta x into delta k is greater or equal to 1 by 2 if the h squared cancel out each other, and you will get the very beautiful relation of quantum mechanics, that is the uncertainty in wave number and uncertainty in position should always be greater than half, always be greater or equal to half. So this would be my equation number third, right? So now I'm just manipulating things in a messy way. So we can write uncertainty uncertainty is. So I want to write uncertainty k, that is the uncertainty of wave number is in the form of derivatives, or you can say derivative or derivative, whatever you say. So this will be the uncertainty in wave number, and this will be the corresponding uncertainty in wavelength. So always keep this thing in mind, that the uncertainty is always positive. From here you can also see the uncertainty always positive. So the any sign we get negative here, we can just take the magnitude of that component, right? So I get delta k is d upon d lambda, and what I have there, that is k is nothing but a 2 pi upon lambda. So that is 2 pi upon lambda into delta lambda. So delta k is, if I take 2 pi common and get, right, 1 over lambda is lambda inverse, it does make sense, and you get delta k is minus 2 pi upon lambda square delta lambda, right? So this would be my equation number 4, and I am taking its magnitude because the uncertainty came out to be here as negative, so I am taking the magnitude. So you can use equation 4 using equation 4 in equation number 3, right? So you will end up getting delta x into 2 pi upon lambda square into delta lambda greater or equal to 1 over 2. So you can actually take your things out from the box here to there, that is lambda square upon 4 pi. So you can actually see from here the product of uncertainty is directly proportional to the wavelength squared. The uncertainty, the product of uncertainty grows and increasing as you increase the wavelength of the particle. So this would be my equation number 4th. Sorry, this is 4th. This would be the equation number 5th. So this. So I can manipulate something very much interesting. Delta x into delta lambda is greater or equal to lambda square p square by 4 pi p square, and it makes sense because I had taken p square in upside and I have to put p square in downside. So we get delta x into delta lambda is greater or equal to. So from de Broglie hypothesis, we can conclude that the product of lambda and momentum is nothing but the Planck's constant. So I can write here h square upon 4 pi p square, right? So again you will end up getting the new relation, that the uncertainty goes on decreasing as you increase the momentum of particle. Yes, very bizarre quantum world, right? So this would be my equation number 6. So I am rubbing the right hand side. I am hoping that the focus is very much good. Okay, so I don't know actually whether it is from relativity or it does actually came from relativity. Whether it is special or general relativity, I really don't know. That from relativity I am using from relativity. From relativity, we can write the total energy squared is m naught c squared, the rest mass energy squared, plus p square c square. This is the energy term, total energy term of any particle within the motion, right? So, and what we were getting from here is we want the momentum term, because I have momentum term here. So I am getting e squared minus m naught square c power 4 upon c square is my p square, and this would be my equation number 7. So I am using 7 in 6. So I will end up getting delta x into delta lambda is greater or equal to h square upon 4 pi, right? H square upon 4 pi, and in terms of p square I am going to write e square minus m naught square c power 4 by c squared, right? And again the c square term will end up getting upward, so h square c square upon 4 pi. So I am just manipulating something very very familiar, e square into m naught square c power 4 by m naught square c power 4 minus m naught square c power 4. It does make sense because the same thing that I have already done in the momentum term, right? So I am end up getting delta x into delta lambda is greater or equal to h square c square upon, if I take m naught c square and m naught square c power 4, from these two I will end up getting 4 pi m naught square c power 4, and I will end up getting e squared upon m naught square c power 4 minus 1, right? So again I'm going to rub the right hand side, and let's see what will be the final result. So I'm already saying that I haven't derived anything basically new. I'm just stick with the old idea with the known results. So this is not my equation, right? Or whether it is not the modification on the Heisenberg, whether it is or not, I really don't know, because I am an undergrad student and I really don't know about that. So I had here, so if you look up here, you will get 1c squared and c power 4 cancel out, and you will end up getting delta x into delta lambda is greater or equal to h square upon 4 pi m naught square c square e square upon m naught c squared squared minus 1. So it makes sense. So we have a very famous relation, that Compton wavelength, that is h upon m naught c, and here you can see that we have h upon m naught square c square. So I can write here delta x into delta lambda is greater or equal to lambda c square, that is Compton's wavelength squared, divided by 4 pi e square upon m naught c squared squared minus 1. So it actually makes sense to you. This is the known result from the experiment, that the quantum scattering associated with the X-rays. So if you know about the relativity, so the energy is nothing but gamma factor, the Lorentz factor, time mc square, m naught c square. The gamma factor times m naught c square. So if you take E upon m naught c squared as gamma, you will end up getting gamma, and if you square this, you will end up getting m naught square c power 4. You will end up getting the same result. So you can actually substitute gamma square is E square over m naught square c power 4. So you can actually substitute here delta x into delta lambda is greater or equal to lambda c squared upon 4 pi gamma square minus 1. So if you had already seen my previous video, that I had actually derived this form of equation, delta x into delta lambda is greater or equal lambda square, lambda c square into 8 pi gamma minus 1. So I am going to make it this second equation, let us say it's equation number b and equation a. I am going to make the equation b as the special case of equation 1 under our classical assumptions, right? I hope it is making sense to you, because I hadn't used something very much strange that is used in quantum mechanics, like the momentum operator and the position operator and the energy operator things. So I'm just making physics looks more beautiful classically, algebraically, right? So we had the equation a is delta x into delta lambda is greater or equal lambda c square upon 4 pi, and you can manipulate it, gamma minus 1 gamma plus 1. Okay, so from this result you can say that gamma cannot be equal to 1. So we can conclude that gamma does not equal to 1. Gamma does not equal to 1. But for our relativistic, for normal speed, for normal speed, meaning normal speed means the speed of light is very much greater than the speed of particle, then the gamma is actually, the gamma is actually nothing but 1 over under root 1 minus v squared over c squared, right? So if the velocity term is very much less, then v square upon c squared tends to 0, and you will end up getting gamma is 1. So if this term goes on decreasing, 1 minus 0 is 1, and under root of 1 is again 1, 1 by 1 is 1, right? We are doing just this approximation for this, not for this, only for this r plus gamma plus 1. So if you have gamma is 1, approximate value, I am just taking the approximate sign, approximate value. So gamma plus 1 would be approximately equal to 2, right? The gamma plus 1 term would be approximately equal to 2. And now look at the equation here. Delta x into delta lambda is actually greater or equal to lambda c squared upon 4 pi into, so gamma plus 1 is nothing but our 2, and this is gamma minus 1, and this implies delta x into delta lambda is greater or equal to lambda c square upon 8 pi gamma minus 1. So you can actually say that the equation first is the general form of the position wavelength uncertainty, and the equation B is the special case of one when the special condition is applied, that is v squared over c squared tends to 0, meaning the v squared is very much less as compared to c. So this is the classical result. So this is the classical result. This is for normal speeds. The speed very much less as compared to the speed of light, right? Okay. So we get classical term. This would be our general form. This would be our general form, and the classical form. This would be our general form, and the classical form is delta x into delta lambda is greater or equal lambda c squared upon 8 pi gamma minus 1. Okay, this is gamma minus 1. So you can actually replace gamma minus 1 is very much interesting thing if we are allowed to expand it. So you can actually manipulate it like the way like gamma is, we have 1 over under root 1 minus v squared over c squared, right? And we have gamma squared is 1 over 1 minus v squared over c squared. So if you take the v squared over c squared, you will end up getting 1 minus v squared over c squared raised to the power minus 1. So here gamma square is nothing, and if you expand it using binomial expansion, you will end up getting 1 plus v square over c square, right? Plus, like goes on, just look at me. 1 plus v square over c square plus v to the power 4th upon c to the power 4th, and so on. So you can actually neglect this term because if they are higher, the speed of light is very much high. So you can approximate gamma up to 1 plus v squared over c squared, and you will get v gamma minus 1 approximately equal to v squared over c squared, right? So from this general form, you can write delta x into delta p greater or equal to lambda c squared upon 4 pi. So this is v squared over c squared, right? So delta p into delta lambda, delta x into delta lambda is greater or equal to, you can write it as h square upon 4 pi m naught square c square v square into c square. This goes offside and you will end up getting this result. So delta x into delta lambda is greater or equal to h square upon 4 pi m naught square v square. So this might make sense to you. This is the classical result. And even if you have the rest mass, this particle only apply for the massive particle as compared to photons. This does not apply to the photon, right? For the photon, you have to replace energy term as in terms of energy. So it does not have rest mass. So for photon, you can actually manipulate things. The momentum, you have E squared is m naught squared c power 4 plus p squared c squared. So for photon mass, rest mass is 0. So your E upon c squared is your p squared. So you can actually make it work for photon also. So you can do it by yourself. I am not doing that. So this is the classical result. So the uncertainty goes on increasing as the momentum increases, the momentum is increased by increasing the velocity. So if the velocity increases, the uncertainty again goes increasing. So this would be our general form, general form, general form, and this would be our special form. So lambda c square upon 8 pi 8 pi gamma minus 1, right? If you don't understand the approximation, you can also approximate in terms of gamma minus 1. You can also actually represent it in classical way, that is, you can write it as here. So why I'm not using gamma equals 1? Because I had earlier told you that the gamma does not equal 1, but we're just doing the approximation for the very much lower speed. So in that sense, it might make sense to you, and I hope you might have understood a little bit of this idea. For that, bye bye.